Okay, so we're back at it. Continue with the blade element momentum theory. Apologize that this video is now almost 4 months after part one, but things got busy, though I still wanted to come back and finish this. So if you go back to video one, you'll recall that these are the two equations we derived. We did a linear momentum balance to get the first, an angular momentum balance to get the second. And then we added this term here, F, that we saw was this correction factor for primarily tip losses of those. Sometimes we can also include some hub losses just because of the finite nature of propeller. It's not an infinite blade. Okay, so blade and momentum, we've covered the momentum part. We're now going to cover the blade element part of this theory. It's actually pretty straightforward. There's really no new theory. We just have to be careful with our velocities. It's really just 2D airfoil theory that we're already well familiar with. So let's look at a cross-section of the blade. So let's imagine this always takes a little bit of time to orient yourself. First time you look at these, let's imagine that the hub of my propeller is into the page. So I'm looking at towards the tip, or I've cut a slice of my blade. So I'm looking at a cross section and it's rotating. Let me draw something here. So this velocity vector here would be v infinity. So this would be spinning around kind of like this. Velocity is coming this way. If I'm a propeller, that means I'm on a plane, I'd be flying up this way. Okay, so at this instant in time, right, this is the hub into the page, blade tip coming towards my face out of the page. I'm looking at that airfoil and my blade is rotating this way, right? So the velocity that I see relative to my blade is this omega r, but I'm rotating this way. So this is that plane of rotation, right? That straight line. So imagine I'm just coming down and around this straight line here, right? So take a minute, try to orient yourself there. Last time what we saw though is that the rotor at the disk doesn't see v infinity. It's accelerated a little bit, right? It's v infinity far upstream. It accelerates to v infinity times 1 plus a at the disk, and then it accelerates further to 1 plus 2a far away. So now we're at the blade disk. We use 1 plus a. Similarly, we saw that the the tangential velocity is decreased by this unknown factor a prime. So a and a prime, variables we don't know, we just know that it's going to be twice that value in the far field. Okay, so those are the two velocities that are coming in. It's a little bit different than what we've looked at with just wings. Usually with a wing, right, I've got an airfoil and all I've got is just say v infinity, and it's fairly simple. But in this case, I've got two velocity vectors. I've got one from my free stream, one from rotation, and the combination of those two, right, if I take the vector sum, add this vector to this vector, and I get this total vector w. This is my inflow vector or inflow velocity. We'll call this the inflow velocity. This is the velocity that my airfoil sees. So actually you'll notice it's quite a lot like our regular case with the wing, except for this angle of attack was created just from this one velocity, and here it's created by this combination of velocities. So it's a little more complicated, but things look more or less the same. So now you can see that this is my chord line of the airfoil, and so this angle here, that's my, oops, it's not drawn very well, alpha, angle of attack, right? And we call this angle here phi. That's the inflow angle. And then this, let's just use another color just so we can maybe see it a little better. This angle here we call theta. That's just going to be my twist angle. Okay, so let me just write those down real quick. Alpha, this angle of attack as always, and that just follows our normal convention, right? It's the angle between the chord line and my incoming velocity. Phi, call this the inflow angle, and notice it just defines the angle of this velocity vector relative to my plane of rotation. So it's simply defined by these blue vectors here at my velocity vectors. And then theta, that's my twist angle. So that's built into my geometry or my pitch of my blade. So I'm going to twist my blade, and I want to twist it appropriately. Notice if my twist is not sufficient for the expected velocities that I'm going to have, I won't have a positive angle of attack. So I want that twist to be sufficiently positive. So I get a positive angle of attack here. I'm going to be generating lift and such. Okay. So this is something, this theta is something that I'm going to design into my blade. It's going to be part of the twist distribution along my rotor, just like we have a twist distribution along a wing. And I can also potentially change with pitch, which would change the twist of the entire blade all at once. Right, it would rotate about the sub, rotate the entire blade. So we get our first equation here. I want to know my angle of attack. Well, pretty straightforward to see from those angles. It's just going to be my twist angle minus my inflow angle. Okay, so that's first equation that we've got here. But now that we have angle of attack, then we're just basically doing just 2D airfoil theory, right? So I know my angle of attack, I know my inflow velocity. What I'm going to get is, let's draw this again, right? Here's my inflow velocity, W. From the definition of lift and drag, we know that's going to create a force lift in this direction. So this is going to be my lift. I'll just write it as a lift coefficient. And then my drag force will be in this direction. Right, and that's just by definition. And lift is a function of angle of attack and potentially other things like Reynolds number and Mach number. So we could write it like this, that my lift coefficient is some function of angle of attack, and in general, potentially also Reynolds number and Mach number. Similarly with my drag coefficient. And we've seen some methods, we've discussed some methods this semester about how I might calculate these. I could use this panel method with integral boundary layer like we use. I could use a CFD type method that we've looked at. This could also be from wind tunnel data that I've tabulated. Doesn't matter, right? But somehow I need a way to compute this. This is not directly part of the theory, right? We assume that there's just a way that you provide me a way to compute these things, okay? And notice that I already have angle of attack. I've got that. That's the primary parameter. That's the most important. I've got angle of attack. Reynolds number and Mach number may be important, right? It depends. For a propeller, if we get to high speeds, then Mach number corrections will be important, and we'll discuss those a little bit more next time. Reynolds number, often, you know, that's going to be kind of built into our data, and we usually won't vary too much, so it may not be important to conclude that, but there's also Reynolds number corrections we could add in. So typically, the most important, right, at a minimum, we really just need this, right? CL and CD as a function of alpha. Although, again, a better model might have a three-dimensional spline that's a function of Reynolds number and Mach number as well, or has some corrections built in. Again, we'll talk about those next time. Okay, so got angle of attack, so I can look up, compute, lift, and drag, right? And again, this may be something I've already computed for an airfoil. I know what my airfoils are, so I can pre-tabulate that data and just fit a spline. So this is a very quick, easy calculation. But as we'll see, what I want is not necessarily lift and drag. I'm going to need these forces, CN and CT, right? My normal and tangential forces. Those are the ones that I care about, because for every angle on the blade, right, every blade is going to be twisted at a different angle, have different angle of attack. So the lift vectors are going to be pointing in different directions along the blade. And I want to get those all in the same, I want to get the components in the same directions across my entire blade. So I'm going to get this normal force, tangential force. Well, if we look at this angle phi, which we defined just before, just the inflow angle, you can see that that is the same angle here, same angle here. So this is just a simple coordinate rotation. So it's going to be Cn is Cl cos phi minus Cd sine phi, and Ct is Cl sine phi plus Cd cos phi, right? So just did that rotation. Okay, so got our angle of attack. From angle of attack, we got lift and drag. From lift and drag, we rotated. We got normal and tangential forces. Okay, so let's again look at this airfoil once more. At each section, I'm computing my normal force and a tangential force. And if we back out to the macro view, remember what we're after is thrust and torque. This normal force is in the direction of thrust for my overall rotor, right? So I just need to sum up these thrust, this normal force along the entire blade. So the normal force per unit length or unit radius, right? So this is the force per unit length, is just going to be given by the definition. If if I just unnormalize the normal force coefficient, right? Cn, so normal force is going to be normalized by its dynamic pressure, 1/2 rho W squared. I need to use the W, right? Because that's the relative velocity that I see. So let's just draw W again. That's the velocity that I experience, and also by some reference area. But in our case, this is a force per unit length, so we just need a length. So I'm going to put a chord. So that's the normal force generated by this propeller. Okay, so let's say I've got this propeller. Here's the front view, right? So it's got a couple blades, and then here's the side view, this propeller, and it's generating, each blade, right, is generating this normal force in this direction. So my total normal force is actually going to be multiplied by B, where B is the number of blades. Right, so if I had one blade, that would be it. But if I have three blades, then they're all, in this simple case, let's say the same. Well, they'll generally be the same, but I mean the same inflow conditions. Then I just need to multiply by the number of blades. Okay, so that gives me the normal force per unit length for one blade, and the thrust then is just going to be, well, actually, no, let me write it this way. Let's just write that is the normal force, but my thrust, rather, the total thrust that here's thrust, this direction, right? That my propeller experienced is that normal force times number of blades. Okay, so that's maybe a little cleaner way to write it. All right, for the torque then, it's going to be pretty much the same. Let's first write what my tangential force is. This is going to be confusing because I've used T for thrust and T for tangential. So let's say I'm going to call this axial for now. Okay, I'll call this my axial force instead of tangential. It's going to be the same thing. I just got to unnormalize CT times 1/2 rho W squared times C. That's this force along this plane of rotation here, right? Okay, so that's the force. And let's look at where it would be, right? This is along the rotation axis of the blade. So if I was looking at this blade here, for example, it would be like in this direction. So the torque that I experience is going to be R cross F, right? So the torque is R times A, or in other words, it's R times CT times 1/2 rho W squared. C, that's the torque for one blade, and then again, I need to multiply by the number of blades. Okay, so then I have to multiply by B again. So that gives me an expression for thrust and an expression for torque. I'm going to write them again a little more cleanly here. Thrust is B times Cn 1/2 rho W squared C. Torque is B times R times CT times 1/2 rho W squared times C. Okay, so great. So now, just like last time, we got an expression for thrust and torque from momentum theory. Now we have an expression for thrust and torque from blade element theory. And now we're going to be able to equate them, okay, from these two different theories. But before I do that, one last thing, I need to specify what W is. We know what it is, but I just need to be a little more explicit, right? It's the combination of these two velocity vectors. So I can take the magnitude of this thing, square it, plus the magnitude of this thing squared, sorry, and then add those together, square root, that gives me W. So just to write that out explicitly, W is the square root here of V infinity 1 plus A squared plus omega R 1 minus A prime squared. Okay, great. So as said, we now have these two pieces. We got thrust and torque from momentum theory, thrust and torque from blade element theory. We can now equate them to get our blade element momentum theory. All right, so let's just do that. Thrust, okay? And both were thrust per unit length. We just did that one per unit length, but remember before we did the momentum for this little annulus, so it was per unit length as well. So before, our first equation that we got from momentum theory for thrust was 4A times 1 plus A times rho V infinity squared times, let's go back here. I think I wrote it a different way. Yeah, pi times R times F, that's the area. We use the area of this little annulus, this little thin disk, pi times R times F, okay? And this equals our momentum theory. which we got B times Cn, this one right here, times 1/2 rho W squared times C. 1/2 rho W squared C. Okay, that's it. So again, thrust from momentum theory, thrust from blade element theory, and we're equating them to each other. All right, so we can simplify this a little bit. A few things can cancel out. Rows can cancel. What we're going to do is we're going to combine some terms. So we're going to define this quantity here. I'm going to define this quantity sigma prime as B times C over 2 pi r. And there'll be one reason is that it appears here, right? I've got a B, a C, a 2 on the bottom, and I can bring this pi r over, but it has a kind of physical meaning here. We call this a local solidity. And so imagine that, here's my propeller disc. Well, that was bad. Let's draw these 3 blades here. Imagine I took my little annulus here, right? We're taking a force per unit length. So I'm looking at one radius. I draw this circle. I want to know how much of that area, or really it's kind of a distance, is covered by blades relative to that that's not, right? So in other words, the distance along the circumference of the circle is 2 pi r. So that's that denominator here. Well, how much of that circumference is covered by blades? Well, that's this part plus this part plus this part. So it's the chord length, the local chord length, times the number of blades. So that's the numerator. So if this was 1, that would mean locally the whole disc there, or this little circle, was completely covered by blades. No air could pass through. So just tell me the ratio of coverage here. You'll also see total solidity. Sometimes it won't appear directly in this theory, but it's a useful quantity that appears. We would not have the prime. Total solidity would then be the area of that full disc, right? So how much of that is covered by blades? So it'd be, what's the area of these blades? So integrate this chord over the blade. So basically my projected area, or my area of my blade, times the number of blades divided by pi r squared, right? That'd be my total solidity. Same kind of meaning, but it's over for the total disk, whereas this is just per local radius. Okay, so with this definition, that was a bit of a side, right? You can see that some of these terms are going to appear there. This is going to then reduce to the following. I'm gonna leave these terms on the left side. 4a, 1 plus af. I'm gonna move this over. I'm gonna move these over. And I get this new term, my local solidity, times my normal force coefficient, times this ratio of velocities, W over V infinity squared. Okay. Torque, do the exact same thing. Let's take our expression for momentum theory, 4a prime, 1 plus a. Let's go back to it real quick. Rho and that stuff. So let's write that down. Rho, I had an omega. Oh, let's see, there was a V infinity omega r squared pi rf. And then I equate that to what we just barely computed from blade element theory, which has got a B, an R, a CT, 1/2 rho W squared C. Okay, again, few things cancel out, not a lot. Some rows cancel out. One of the R's cancels out. I'm going to then have that solidity term again, right? Because I've got a B, a C, a 2 in the denominator, and the pi, and one of these R's I'll bring over. Okay, and so if I do that, I get 4a prime 1 plus af equals sigma prime CT times W over V infinity times W over omega R. Okay. So these are my 2 equations that I've got. This one, they look pretty similar, but they're a little bit different. All right, so this is good so far. I've got 2 equations. I have in principle 2 unknowns, right? The 2 things I don't know are a and a prime, but that's not quite so simple because actually W, well, W depends on a and a prime, but a and a prime, let me get to that in a second. So, okay, so we've got these 2 equations. We're still trying to solve for our unknowns. And actually, I'm going to simplify this a little bit further because I've got these W things that I don't like. I want to get things more in terms of just these A and A primes. So let's look back at our velocity vectors. I'm just going to write them again. Remember, we've got, it's probably too big. V infinity, 1 plus a, the free stream. We've got this rotation velocity, omega r1 minus a prime. The sum of those two together, the vector sum, creates my inflow velocity, w. So I'm going to, and this angle here, we defined as phi, okay? So I can relate w to these other velocities. I could do it in one of two ways, right? So for example, I could see that the sine of phi is this opposite over hypotenuse. So that's v infinity 1 plus a over w, or in other words, w over v infinity, which is one of those terms that appeared in my equation, is 1 plus a over sine phi. Or I could use the cosine. The cosine is omega r1, oops, omega r1 minus a prime divided by w, or I could see that w over omega r is equal to 1 minus a prime over cos phi. Okay, so I'm going to take these things and substitute them in. I've got this w over v infinity, I'll substitute in here, and then for w over omega r, I'll substitute in this thing. Okay, and when I do that, this is going to make this simpler. Some things are going to cancel out. So I had a 4a 1 plus a f equals sigma prime cn w over v infinity squared. Okay, this was my thrust equation. Just rewriting it again. Okay, note again, w over v infinity, I'm going to substitute this in. Notice there'll be a 1 plus a squared now, which is one of those is going to cancel one of these. And then I'll have a sine squared on the bottom. Okay, so I substitute that in. I'll do a little bit of algebra. I'm going to skip it just because there's nothing really exciting about it. But I can then solve, by doing that, I can actually solve for a, and it is as follows: 4f sine squared phi over sigma prime cn minus 1. And obviously there's a lot of different ways I could algebraically rewrite that, but this is the important point, is I can rearrange for a. Same idea with torque, right? I've got a 4a prime 1 plus a f equals sigma prime ct, and I had a omega over v infinity, or sorry, not omega, w over omega r, right? And then I take one of these and I plug them in, and notice that the 1 plus a is going to cancel one of these. And then I've got a 1 plus a prime, and I can bring all the a primes to one side and kind of solve. And I'm going to get the following: a prime equals 1 over 4f sine phi cos phi over sigma prime ct plus 1. Okay. All right. So here's where we're at. Looks like we have explicit equations, though it's not quite the case, as we'll see. But I had my two unknowns. Remember, I had two equations, got them from these two different theories, equated them. And I could solve for my two unknowns, which I've done. I can solve for my axial induction factor and my tangential induction factor. The problem is this, though, is that these are not actually explicit because phi, for example, actually a lot of these things are going to then depend on phi. Phi, right way back here, this inflow angle. To get the inflow angle, I need to know the angle of attack, or I need to know theta, or to get, let's just say, even to get phi, I need to know that's completely defined by these velocity vectors, right? And those velocity vectors are defined by what a and a prime are, but I don't know what those are. That's what I was trying to solve for. So I've got this sort of circular dependency here, and without knowing phi, I don't know the angle of attack, which means I don't know what lift and drag, which means I don't know CN, CT, so I can't actually compute CN and CT that appear in these equations. So these are actually implicit equations. This is classically, this has been solved commonly with like, say, Newton's method, because they're, two implicit equations. That's no big deal. We can plug in a Newton's method, root finding problem, solve for a and a prime iteratively. Or you could use the fixed point iteration, right? We could make a guess for a and a prime. From those guesses, we then get new phi, and then we can compute a new a and a prime, and then keep doing that until things don't change. The problem with these methods, though, is that they don't always converge, which is not such a big deal for analysis usually, because if it doesn't converge, you maybe perturb it and try again, or you throw out that point and go to the next one. But if you want to do optimization and design propellers, you need this to solve quite reliably. And so I developed an alternative approach. I'll show you right now. It's fairly simple, but it's much more robust because we can then reduce this to one equation, which means we can use a bracketing method and solve it reliably. So the key insight here is that rather than thinking of A and A prime as the unknowns, right? If I know A and A prime, that defines those velocity vectors for me. But alternatively, I could think of W, this magnitude, and phi as my unknowns, right? The magnitude and the angle, rather than these two components, that also defines my velocity vector. If I do that, though, W doesn't directly appear in these equations, at least with some tiny caveat that we can iterate over if we really need to. It's in almost all cases not important. Phi is the one that directly appears. So if I use phi as my variable, then this becomes a one-dimensional problem. So another way we could write this, there are many ways to formulate this. I'll just show you one. Instead of doing sine and cosine, let's look at the tangent so I can just directly relate these two. So if I do that, I could say the tangent of phi is v infinity 1 plus a over omega r 1 minus a prime. So that's the key equation. As I said, you can rearrange this tons of different ways, right? I'll show you the way I derived it. I've seen other people since rearrange it in different ways, which is the same thing. You just, you can move things around or express A in terms of some of these other things, right? There are a lot of ways you can rearrange it, but same idea. So I'm going to rearrange this. I'm going to move everything to one side and set it equal to 0. So I could say that sine of phi over 1 plus a minus v infinity omega r cos phi 1 minus a prime equals 0. So this is the same equation. I just moved everything to one side, so it's in the form of a root finding problem. I did it in this form. It has some advantages in terms of where singularities occur. I'm not really going to get into it, but this is a nice way to do it. Again, there are other ways you can do it. The nice thing about this, though, is that this is one equation, right? We call this a residual function of phi, one variable. So I just need to solve a root finding problem for one variable phi. Once I have phi, and the reason why that's the case, right, is that a is a function of phi, and a prime is a function of phi. So everything in here just depends on phi, rather than having these two equations from a and a prime. And again, the reason why this is powerful, even though we've only gone from two equations to one, is that root finding with 2D is the same as root finding with 100D, at least in terms of method, right? Not in terms of time, but in terms of method. Whereas if I go to 1D, I can use bracketing methods, like a Brent's method that uses bracketing with interpolation, so it's very fast, but it's still guaranteed to always converge, always get my answer as long as I can find a bracket. Typically, I have a whole paper that discuss, or two papers actually, that kind of discusses if you really want to get into some details, but normally the solution bracket is going to be in this range here, 0 to pi over 2. You can just do that, but in my codes now, I use a marching method so I can make sure to find the bracket. That just allows me to use any methods. You can generalize this to all sorts of corrections. You can find that bracket, and then this is just going to work. Okay, but again, for our simple purposes here, you just set this bracket, and this is going to work. Okay, so let's review this procedure here. So here's how you would do this, right? So you create a function. I'll call it r of phi, and that's our residual function. So phi is coming in. So since phi is coming in, I can now compute my angle of attack, right? Because I know the twist. So then now I can compute CL and CD. They're a function of alpha, and again, maybe Reynolds number and Mach number. I'll just write angle of attack for our purposes here in this simple case. Okay, so I got CL and CD, and then CN is equal to CL cos phi minus CD sine phi, and CT is equal to something like that too. Then I can compute A and A prime, right, just from these formulas here. Okay, so A is equal to whatever it was. I'm going to write it yet another way. I'm just factoring things around. Sigma prime over Cn, 4F sine squared phi minus sigma prime Cn. So this is the same thing. I don't know why I just keep writing different ways. I multiply top and bottom by sigma prime over Cn, right? So it's one way to do it. A prime, also another expression. And then I'm going to return my residual, right? And this is the thing I'm trying to get to be 0. Sine of phi, that's this equation here. I'm going to return this thing. Sine of phi over 1 plus a minus phi infinity omega r cos phi over 1 minus a prime. Okay, so here's this thing. I don't know what the phi I should put in here. I could put in a guess. I'm going to compute this, and I'm going to get something that's not 0. So now I just put this in a root finder, right? And again, Brent's method is a good one, but you could really use any 1D root finding method. You could even use fixed point iteration if you wanted to, right? You guess it, you don't get 0, or you could even iterate, right? I mean, there are a lot of ways you could do this. It's just one dimensional. You could plot it and look at it, okay? So however you do it, you iterate to get the phi that now brings this residual to 0. Okay, and again, a root finding method will do that for you. So you do this, you repeat this for each section on the blade. So I'm at a specific section, a specific point on the blade. I solve this thing. I find what is the phi prime that makes this 0. Once I know phi prime, then I know what my actual a and a prime are, right? I just go back and compute. I just go back and run this expression one more time, but now that I know the right phi prime, I have the right angle of attack, the right lift and drag, the right normal force, the right induction factors. So I save all those. I compute W, right? W equals the square root of a bunch of stuff. And I get my thrust per unit length. It's B times Cn times 1/2 rho W squared times C. Get my torque. It's a similar expression. And now that I compute this at one station, I repeat that for every section of the blade. And then to get my overall thrust, I just integrate, right? I integrate from the hub to the tip. Same with torque. I integrate from the hub to the tip. And if I want power, it's just torque times my rotation speed, right? So I want to know how much power I'm expending. In this propeller case was a wind turbine. I want to know how much power I'm producing. And that's the method, okay? And one last thing I'll show here. Often we like to non-dimensionalize. I've been writing in terms of thrust and torque. We often like to report thrust coefficients, torque coefficients, power coefficients, and so on. Conventions are different for everything. This theory will work for, all of these things. I can do it for propeller, I can do it for turbine. I can even do it for like a rotorcraft helicopter type thing, but each of these fields has their own conventions for normalization. And sometimes even within a field, you'll see some differences. So be careful when you look up these coefficients, make sure you know how they're normalized. I'm just gonna flash this real quick. These are just conventions, one convention, a common convention for propellers. I find the wind turbine conventions much more convenient, intuitive, but for whatever reason, here's what they are for propellers. Take thrust and normalize by density. This quantity n, which is a little bit strange, it's a rotations per second. So it's not RPM, rotations per minute, and it's not radians per second, omega. It's rotations per second. So it's kind of halfway between them two. So we could take radians per second, divide out by the 2 pi radians. So then I would get rotations per second. Okay, so that's what n is, and then d is my diameter. This is an important, as we've talked about many times in the semester, right? Non-dimensional numbers, super important, but they're useful for things, right? That I can now plot these thrust and torque values. For example, I might plot my thrust, and what I'll typically plot them is as a function of advance ratio. So maybe I plot how my thrust coefficient varies with advance ratio. Advance ratio is this other non-dimensional parameter. It's not quite, it's like a factor of pi different, but it's my forward velocity, that inflow velocity, divided by something that's like my rotational velocity. This is not omega r, right? This, that would be what it is in the wind turbine and helicopter community. Actually, in the wind turbine community, it's omega r over v. But anyway, omega r is not quite n over d, right? To get that, I would have to divide this by 2 pi, multiply by 2, right? They differ by a factor of pi, but basically it's this ratio of forward to rotation speed. So that's a typical quantity that I would plot these thrust, torque, and power coefficients as a function of, and maybe my efficiency. So I want to see how my efficiency varies with advance ratio. Again, this is an important thing to look at as opposed to just speed, because speed doesn't tell me anything. It's not my rotation speed that matters. It's what's my rotation speed relative to how fast I'm flying. right? It's that advance ratio that's going to then determine my efficiency, not just purely rotation. Okay, so that's it for part 2. Went through the method. I think we've talked about everything you need to kind of implement the basic method. Next time we'll do a part 3 where I'm going to talk about some corrections that are needed. So for example, it turns out that airfoil data that you would get, just regular 2D airfoil they're used to getting, is not quite good enough because we have a rotating blade, and that actually affects the physics. The behavior is not quite the same as a normal sort of 2D static case. Okay, and then there are a few other considerations like that that I'll discuss, but this is kind of the main implementation or methodology. And that will be sooner than 4 months, hopefully by tomorrow.